So it turns out that degenerate matter, in general, we'll see in other forms when we talk about the neutron stars. Degenerate matter has some very unusual properties. First, it turns out that the pressure does not depend on temperature like in normal matter, right? I mentioned before that in normal gases, the two go together. If the temperature goes up, then the pressure goes up, just like in the air in the car tire, right? After you've driven the car for a while, it warms up because the work done by the force of friction is transformed into heat, and the pressure in the car tires goes up. But with degenerate matter, that's not the case. The pressure does not depend on temperature, but only on density. And it increases with density. And it turns out, our calculation shows that, for instance, our fourth-year students can do. It shows that you can show that it increases with density. And the second feature is that the larger mass has smaller size, smaller radius. And in fact, this property is related to the fact that the pressure increases with density, because if I have more mass, I need higher pressure to support the object, right? But I can get that higher pressure only if I increase the density, which means that that given mass has to be packed in a smaller volume for the density to go up. So as I keep on adding mass to the degenerate object, it actually shrinks in size. So we should contrast that to the behavior of ordinary matter. Okay, so here is the relation between the radius measured in the units of sun's radius versus mass. And this is how the normal matter, or say the stars on main sequence, how they behave, how the radius depends on the mass. The bigger the mass, the larger the radius, right? So this would be dependence on, of size on the mass for normal matter, since a main sequence star. And we know that we have intuitively, it makes sense to us, right? I mean, over the holidays, if you eat a lot, then, you know, your radius is going to go up. So that's how the normal matter behaves. But now let's look at the corresponding diagram for degenerate matter. For degenerate matter, say a white dwarf, we have the opposite, that as the mass goes up, the radius is decreased, and eventually it becomes zero, which tells you that there is a maximum mass that the degenerate object can have. It's so-called Chandrasekhar limit. So this is how the radius versus mass dependence looks for degenerate matter. Okay? And the reason for that, again, is the fact that the pressure depends only on density, does not depend on temperature. So as mass increases, you need higher pressure to support the object that is now heavier, right? It has more mass. But you can realize higher pressure only if you increase the density of degenerate electrons, meaning you have to pack them into the smaller volume. So that's why the object shrinks, in order to create higher pressure. And the maximum mass that a degenerate object can have is called Chandrasekhar limit. I mean, degeneracy term is not really, it has no moral or character connotation. It's just the way it arose when people looked at the properties of electrons when they start occupying all the lowest available energy levels, but obeying Pauli principle so that you can put at each energy level only two electrons. One would spin up, the other one would spin down. And for a white dwarf, it turns out the precise value of the number depends on what the object is made of. And for white dwarfs, they are made of mostly of carbon nuclei and some oxygen nuclei. It's 1.4 solar mass. So Chandrasekhar, or as he was often called in first Britain and then later on in North America, Chandra, right? East Indian, complicated name. People just, and he didn't mind it, they called him Chandra. He was actually, when he came up with this, he was only 19 years old. He finished his undergraduate studies in India and was accepted to do the graduate work at Cambridge. And while traveling on ship from India to England, he started thinking about this problem and worked it out. And when he got to Cambridge, he was asked to give a seminar about that. And he was ridiculed. People didn't believe it. Among most influential people was Sir Arthur Eddington, one of the leading observational astronomers of that time. However, he was right. He stuck to his guns, and later, much later, he was awarded the Nobel Prize for this work. So a lesson here is that if you honestly believe that whatever you have come up with is correct, then you have to stick with it, regardless of what others say. Doesn't matter. So for a white dwarf, it is 1.4 solar mass. I also want you to note that the bigger the mass of the white dwarf, the smaller the radius, right? So for instance, a white dwarf of a mass equal to 1 solar mass, which is still within this range, it's less than than the Chandrasekhar limit. He has a smaller radius than, say, a white dwarf whose mass is only half of the solar mass. Remember, the bigger the mass, the smaller the radius. It turns out that the radii of white dwarfs fall in the range from about 0.008 of the sun's radius, from, as I said, 0.008 radius of the sun. In these units, the radius of the Earth is just slightly bigger, 0.009 of this sun's radius to 0.02 solar radii. And as I said, the radius of the Earth is about 0.09 solar radii. And the observed masses of white dwarfs range from 0.17 of the solar mass up to 1.33 solar masses, but most of them have masses in the range between 0.5 and 0.7 solar masses. So from 0.17 solar mass to 1.33 solar mass. Okay, none of these numbers is exceeding Chandrasekhar limit. So remember, the higher the mass, the smaller the radius. So these most massive white dwarfs have the smallest radii. So the correspondence would be like so and like so. Okay, so we see that the most massive white dwarfs actually are comparable in size to our Earth, right? The most massive ones have a radius about 0.8% of sun's radius, which is not too different from the radius of the Earth. So you can often read a statement that the typical size of a white dwarf is comparable to Earth. Well, not quite so, right? Because there is a whole range of radii, and the smallest ones, the most massive ones, are indeed comparable in size to Earth, right? And I should add here that most white dwarfs have masses between 0.5 and 0.7 solar masses, with a maximum around 0.6, roughly half of the sun's mass. Okay, so you can ask the question, quite legitimate, fine. Okay, they are dim because they are small in size. Remember the luminosity, those of you at least who took astronomy 1P01 will recall the Stefan Boltzmann's law, where the luminosity of a source depends on the surface area, that is, it's proportional to the radius squared of the source, and the temperature to the fourth power, right? So they are small, and as a result, they are not very luminous. But they're very hot. You know, that dead carbon core of a medium-sized main sequence star is very hot. Its temperature is several tens of thousands of degrees. Okay? So it produces light, but the source is not intrinsically very bright. It's not very luminous. But you can ask the question, okay, so why do they produce light if they don't produce any more new energy through fusion? Why are they emitting light? And the reason is that the carbon nuclei, right? The white dwarf is made up of very densely packed carbon and oxygen nuclei, and electrons are roaming around at great speeds, making the whole body electrically neutral. And the speed of the electrons, because they are so compressed, is so high that actually they create enough pressure to support the whole thing, this so-called electron degeneracy pressure. Well, the reason that white dwarfs shine is that actually the nuclei, the carbon nuclei and oxygen nuclei, do not obey Pauli principle. We can put as many carbon nuclei into the same energy level as we want. There is no restriction on the number of nuclei that we can put in a particular energy level. Put here the energies of the nuclei, and here are the separate energy levels, schematic diagram that these nuclei could occupy, right? So here I have energy, and then in any one of these levels I can put as many nuclei as I want. And some of them will be in the lowest energy state, right? Some will be in what we call excited state, and so on. And because the white dwarf is very hot, there are nuclei with very high energy, occupying high energy states. But they can relax, they can drop to the lower energy levels by emitting a photon in the process, by emitting the light. So this one here can actually drop to this level, or it can drop to that level, or it can drop all the way down. And in each transition, it can produce a photon of light whose energy depends on the energy difference between the initial and the final level. Okay, and it's that how they produce light. So they have certain thermal energy that they acquired while being compressed at the end of the main sequence life, and now they are giving up that energy by nuclei dropping to the lower energy states. With degenerate electrons, we have totally different picture. So if I want to make the same type of diagram for degenerate electrons, okay, so here again the vertical scale gives the energy. And then I have now, again, a set of energy levels now for electrons, okay? And this can go on. Now, the Pauli principle tells me that in each one of these energy levels, I can put at most 2 electrons, one with spin or magnetic moment pointing up, and the other one with spin down. And Pauli principle tells me I cannot put more electrons into this single energy levels. Only 2 because they have different spins. And then I keep on going. In the degenerate electron gas, you have this sort of situation where the levels are successively occupied by 2 electrons. And these, in the highest energy states, they can drop lower, right? Because there's no place to go. The parking lot is full. All the parking spots are occupied. If somehow we had degenerate electron gas without very hot nuclei around, right? If I'm to touch these degenerate electrons, those in the highest energy levels might have very high energy, but I would not get burned. Why is that so? Well, because for me to get burned, the gas would have to transfer some of its energy onto me. But it can't lose the energy, because if it was to lose the energy, these electrons in the highest energy state would have to drop down to the lower energy levels. But they have nowhere to go. So I'm safe to touch the degenerate electron gas because, again, of the Pauli principle. No energy can be transferred from it to me. Okay, so eventually all the nuclei drop to the lowest energy states, and therefore the emission of light would stop. And the white dwarf will become a black dwarf. But this happens over a very long period of time, as I said, comparable to the age of the universe. Okay, so I can safely touch a black dwarf. I cannot touch safely white dwarf because in addition to degenerate electrons, I have these nuclei, some of them very energetic, and they can drop into lower energy states. Therefore, they can transfer some of their energy onto me, lose energy, right? Transfer it to me, I get burned, and they drop to the lower energy states. But in the black dwarf, they have nowhere to go. So I can get burned by these energetic nuclei. There is still degenerate electron gas that is supporting this black dwarf, right? But as we discussed, degenerate electrons cannot transfer any energy onto me, right? In spite of the fact that some of them are very energetic. Okay, so white dwarfs have high surface temperature on the order of several tens of thousands of degrees. And being so hot, they emit a lot of energy at ultraviolet wavelengths. Remember the Wien's law, at least those of you who took astronomy 1P01. The wavelength of light at which the body emits most of the energy depends on the surface temperature. The higher the temperature, the shorter the wavelength of the light which carries most of the energy. So white dwarfs are so hot that it turns out that they emit a lot of energy at short ultraviolet wavelengths. And these ultraviolet photons have enough energy so when they hit the atoms in the planetary nebula, they will excite electrons in those atoms into higher energy states. And as these excited electrons relax back to the lower energy states, they will emit photons. But being the particles that must obey Pauli principle, this drop has to be consistent with the Pauli principle. They cannot drop into a level that is already occupied by 2 electrons. They emit photons, or photons. And this process that we mentioned, those of you who took Astronomy 1P01 will recall when we talked about the northern lights, aurora, right? Why do they glow? How do they produce light? Through a similar kind of thing, except the excitation was done by the high energy solar wind particles. Here, it's done by high energy UV photons. And this process of electrons being excited and then dropping back with the emission of photons is known as fluorescence. Okay? And that is how planetary nebula produce the light. If you go back to, I guess, last lecture, or the one before, I can't remember, when we talked for the first time about planetary nebula, I showed the photographs of 2, of ring nebula and helix nebula, and they have spectacular colors, this and that. And that's how they produce that light.